Section 2.3. Let's ask this question. Say you were on a shopping spree and bought 2 pairs of jeans, 3 shirts, and 2 pairs of shoes. How many new outfits, consisting of one of each of those, I don't think you'll want to wear both pairs of jeans at the same time, would you have? Or, they used to have these a lot. Compact Disc Buyers Club, before the advent of iTunes, sends you a brochure saying that you can pick any 5 CDs from a group of 50 of today's hottest sounds for only $1.99. How many different combinations of those can you choose? Or 6 local bands have volunteered to perform at your benefit concert, and there is some concern over the order in which the bands will perform. How many different lineups are possible? Now, these are combinatoric questions where the actual answer that you're trying to get is how many different ways can I arrange a set of things that are organized in a particular way. So that's what we're going to learn here today. So all of the possibilities can be listed and then counted. This is combinatorics. And it involves the fundamental principle of counting and combinations and permutations. These are the various aspects of combinatorics. So just to answer these questions, you could make 12 outfits. You could have 2,118,760 different combinations of the 50 CDs, taken 5. Kind of like a Sonic's different shake combinations, I think. And there's 720 different ways the 6 local bands could arrange themselves. So how did we get those answers? Let's start off with the fundamental principle of counting. Daily life requires a lot of different decisions, and in a series of decisions, you want to know what the total number of possible selections are. So we can do this in a bunch of different ways. We can list all the choices for each category and match them up in all possible ways. That gets tedious, so we use a tree diagram to do this. It's a graphical way to help us keep up with our choices. So a cluster of branches is drawn for each decision. The number of branches is the number of choices. So for instance, if I have a decision of which I have 2 different choices, I have 2 major branches in the decision that I can go down. So that's what I'm thinking about when I'm doing this. So decision 2. And then once I've made decision 2, choice 1 or choice 2, I then have this method can be applied layer on top of this, time-consuming and impractical, especially and you can see how this tree can get very large. They have large numbers of choices. So let's see if we can find a shortcut to determine the number of possible combinations of a particular type. So here we go. If you buy 2 pairs of jeans, 3 shirts, and 2 pairs of shoes, how many outfits are you going to have? Well, there are 3 categories, so there are 3 choices. 1 pair of jeans, 1 shirt, and 1 pair of shoes. So I'm going to put these in order. 1, 2, 3. Now, the order of these decisions does not affect the overall outfit. It just affects how you approach solving the problem. Okay, so for jeans, I have 2 choices, jeans 1 and jeans 2. Shirts, I have 3 choices, shirts 1, 2, 3. So I'm going to go ahead and lay those out there. So if I choose jeans 1, I can choose shirt 1, 2, 3. If I choose jeans 2, I can choose shirt 1, 2, 3. Alright, so we have those other things done. We know that shoes have 2 decisions, shoes 1 or shoes 2. So for each shirt, we draw 2 branches. And there end up being 12 possibilities. So these 3 right here form a single outfit. So that's J1, S1, or J1, shirt 1, shoes 1. A different outfit is jeans 1, shirt 1, shoes 2, and so forth and so on. So there's that first one, and we can list the other 11 possible outcomes there as shown. Okay, so each time a decision is made, the number of branches is multiplied by the number of choices. So there were 2 jeans times 3 shirts times 2 shoes equal 12 outfits. So the generalization of this multiplication process, the basic way to do it is draw a box for each choice, each decision, enter the number of choices, and just multiply across the number of choices. Let's take a look at another example. A serial number consists of 2 consonants followed by 3 non-zero digits followed by a vowel. A, E, I, O, U, for example, ST432E or DD666E. So how many serial numbers are possible given these following conditions? Letters and digits cannot be repeated in the same serial number. So we see the first one up there would be fine, but the one on the right side would not be fine because it has repetitions. Letters and digits can be repeated, so that would be okay for either one of those up there. So how will we figure this out? Serial number has 6 symbols. We make 6 boxes. Okay. And now we're going to deal with each one of these separately, and when we're finished with that, we'll multiply them together. So there are 21 different choices for the first letter, the first consonant. Remember, there are 5 vowels, A, E, I, O, U, so when we subtract those out, we're left with 21 consonants. Okay, since I can't repeat letters in the second box, whatever I choose in the first box, it doesn't matter what it is, whatever it is, I can't choose it for the second box, so that's going to leave me with 1 less. Okay, so 9 digits, non-zero, means that they can be 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's only 9 digits I can choose from, and if I cannot repeat it, then there's only 8 I can choose from, and after I've chosen 2 and I can't repeat, there's only 7 I can choose. And now I have my vowels on the end, A, E, I, O, U, so that's 5. So if I go ahead and multiply that all together, it comes out to be 1,058,400 different serial numbers given this combination. Now if you wanted to do repetition being okay, it would just be 21 times 21 times 10 times 10 times 10, times 9 times 9 times 9 times 5. Okay, and that would give you a few more combinations. Okay, so let's take a look at this one. 3 students are in a bedroom, 3-bedroom house near campus. One of the bedrooms is desirable, has a bath, one has a balcony, and one is very small. How many ways can the housemates choose the bedrooms? Well, 3 decisions have to be made. Somebody gets the room with the bath, somebody gets the room with the balcony, and the last person is left with the small room. So to start off with, we have 3 people in 3 rooms. Now once one room is taken, we only have 2 rooms left to choose from. And once that second room is taken, there's only 1. So there are only 6 possibilities here. So we often see products of this type, 3 times 2 times 1. And this type of product is called a factorial. And we write 3 times 2 times 1 as 3 exclamation point to indicate that it is a factorial. So 4 factorial is just simply 4 times 3 times 2 times 1. And 5 factorial is just 5 times 4 times 3 times 2 times 1. Okay? So these factorials are integers, and whatever it is, you just go ahead and continue to multiply them out. Now note that 0 factorial, by convention, we give a possibility of 1, a value of 1. So let's figure out how we might do these calculations here. 6 factorial, pretty straightforward. 6 times 5 times 4 times 3 times 2 times 1. That's 720. Okay, now what about this guy up here on top? We have to be very careful and make sure that we understand what we're doing here. So I'm going to go ahead and list out 8 factorial and 5 factorial underneath it in the expanded form. And I think it's easy to see that up to 5, they cancel out. 5 over 5 is 1, 4 over 4 is 1, and so forth. So when we do this type of division, we're just left with 8 times 7 times 6, or 336. All right, what about this next one? This one can be a little tricky, so let's go ahead again and list out all of our numbers. Now it's easy to see once again that all of these cancel out. And while it may have been tempting to say 3 plus 5 is 8 and 8 factorial and so forth, you see that does not work that way at all. So we end up with a value of 56 for that one.